A ring of frozen debris sits 2 billion miles away, and every spacecraft we have ever sent toward the stars had to pass through it. Most people have never heard of the Kuiper Belt. Hundreds of millions of icy objects, temperatures at minus 390 degrees, dust particles that hit spacecraft like bullets. We are going to find out why this one region has stopped every mission we've ever planned to deep space. We'll look at the dust that punches through solid metal, the 4-hour communication blackout, the math that says even our fastest probe would take over 25,000 years to reach the nearest star. If you enjoy the journey, subscribe. You won't want to miss what comes next. Buckle up. We begin. Picture a donut, a massive frozen donut wrapped around our entire solar system, billions of miles from where you're sitting right now. That's the Kuiper Belt, and it's real. Scientists confirmed its existence in the early 1990s, and since then every mission we've sent toward the edge of our solar system has had to cross through it. The belt starts just past the orbit of Neptune, the farthest official planet we have, and stretches outward for another 1.5 billion miles. It's not a thin ring, it's thick and wide, like someone stacked hundreds of millions of frozen chunks of rock and ice into a giant puffed-up circle around everything we've ever called home. From the inside, you'd never know it was there just by looking up. The objects inside it are too small, too dark, and too spread apart to see with the naked eye. Even powerful telescopes struggled to spot anything in the belt for decades. Scientists suspected it existed long before they could prove it. Here's what makes it so strange. If you tried to draw it to scale on paper, placing the entire Earth the size of a period at the end of a sentence, the Kuiper Belt would be a ring wider than a football field sitting 100 yards away from that tiny dot. The distances involved are almost too large for the human brain to process. And yet this enormous ring is mostly empty space. The objects inside it are so spread out that the average gap between any two large chunks is millions of miles across. Spacecraft, like Voyager and New Horizons, passed straight through the belt without hitting a single major object. Hollywood got that part completely wrong. There are no tight corridors of spinning boulders to weave through, but that doesn't mean it's safe. The danger hiding inside the Kuiper Belt is invisible, tiny, and moving at speeds that make it far more terrifying than any giant rock ever could be. We'll get to that soon. For now, understand the basic picture. The Kuiper Belt is a vast, frozen outer shell of our solar system. It's made of leftover material from the very formation of the planets billions of years ago. The objects inside it never got the chance to clump together into a full planet. They just stayed frozen out there, orbiting slowly in the dark. The belt sits so far away that light from our star, traveling at 186,000 miles per second, takes over 4 hours just to reach its inner edge. 4 hours at the speed of light to reach the beginning of this place. And yet, in cosmic terms, the Kuiper Belt is practically in our backyard. The nearest star system beyond our own is so far away that placing the belt on a map next to it would make the belt look like a tiny smudge right beside us. The real distances of space start after the belt ends. That gap, the one between the outer edge of the Kuiper Belt and the next star, is where every dream of deep space travel falls apart. The frozen donut is only the first wall, and the next wall is built from something far harder to solve than distance. 2 billion miles. Write that number out. 2,000 million miles. A 2 followed by 9 zeros. That's where the Kuiper Belt begins, right past Neptune's orbit, the point where the last recognized planet in our solar system runs out of road. Now try to picture 2 billion miles using something you actually know. The distance from New York City to Los Angeles is about 2,800 miles. To reach the inner edge of the Kuiper Belt, you'd need to make that cross-country drive roughly 700,000 times, back and forth, without stopping, for your entire life and the lives of everyone you've ever met, and you still wouldn't finish. That's just to reach where the belt starts. Light handles this distance in about 4 hours and 15 minutes. A commercial airplane flying at 600 miles per hour would take roughly 380 years, and humans have never sent a crewed mission anywhere near it. Every single vehicle we've ever put in space that reached this region was an unmanned probe, a machine, sent alone. The New Horizons spacecraft launched in 2006 and reached the belt's outer region in 2015. 9 years of travel at 36,000 miles per hour, and it still hadn't fully cleared the zone. 9 years. For a machine moving faster than a bullet by a factor of 30. Here's where it gets harder to accept. The Kuiper belt doesn't end at 2 billion miles. It stretches outward to roughly 4.5 billion miles from our star. So the belt itself, just the belt, spans about 2 billion miles of width. A spacecraft has to cross all of that before it even touches interstellar space. Interstellar space is the term for the region between star systems. Beyond the belt, past another even larger shell called the Oort cloud, lies the empty gulf between our solar system and the next. That gulf is measured in light years. A light year is the distance light covers in one full year, light moving at 186,000 miles every second. For an entire year, the nearest star system to ours sits about 4 light years away. At New Horizons' speed of 36,000 miles per hour, reaching it would take over 75,000 years. And New Horizons is one of the fastest objects humans have ever launched. So when people talk about traveling to other stars, the Kuiper belt isn't even the hardest part of the problem. It's just the first part, the opening chapter of a story that currently has no ending we can write. The scale breaks something in the human brain when you sit with it long enough. We are used to distances that feel conquerable. Drive a few hours, take a flight, spend a week at sea. Space doesn't work that way. The distances aren't bigger versions of things we know, they're a different category entirely. And the machines we've built, as impressive as they are, barely make a scratch in that category. 2 billion miles to start, 4.5 billion to finish, then 75,000 years of empty dark after that. Every plan for reaching another star begins with crossing this frozen ring first, and the way the belt tries to stop you isn't by blocking your path, it's by shredding you. Every sci-fi movie does the same thing. The hero's ship flies into an asteroid field. Rocks are everywhere. Massive boulders spin past the cockpit. The pilot yanks the controls left, right, up, down, barely squeezing through gaps as chunks the size of houses tumble past at terrifying speed. It looks incredible, and it's almost entirely wrong. The real Kuiper belt looks nothing like that. Scientists confirmed this when Voyager 1, Voyager 2, and New Horizons all passed through the region without hitting a single large object. Engineers tracked each probe carefully, looking for any sign of impact. Nothing. The missions flew through billions of miles of belt and came out clean. Here's why. The Kuiper belt is enormous. Hundreds of millions of objects spread across a ring that spans billions of miles. Even with that many objects, the space between them is so vast that your odds of bumping into one by chance are almost zero. The average gap between major Kuiper belt objects runs into the millions of miles. Picture this. Take a football stadium and place 2 golf balls inside it. Those 2 balls represent large Kuiper belt objects. Now ask yourself, if you walked into that stadium blindfolded and wandered around, what are the odds you'd step on one of those golf balls? Nearly impossible. That's what spacecraft are dealing with. The objects are there, but the space around them is so much larger that flying through the belt without hitting one is the expected outcome, not the lucky one. So the Hollywood version wasn't just exaggerated. It was built on a false picture of how space actually works. But here's what the movies accidentally got right without realizing it. The real danger inside the Kuiper belt is invisible. You'd fly straight through a region full of hazards, and never see any of them. The threat doesn't come from rocks the size of houses. It comes from pieces of ice and dust the size of sand grains, or even smaller, floating in clouds so thin you'd never detect them visually. And those invisible particles are where the actual fear lives. At low speeds, a grain of sand hitting a surface is harmless. You walk through wind-blown dust every day, and it does nothing to your skin. But speed changes everything. Physics has a rule. The energy of a moving object grows with the square of its speed. Double the speed, quadruple the energy. Triple the speed, 9 times the energy. A spacecraft crossing the Kuiper belt moves at tens of thousands of miles per hour. At that speed, a particle the size of a grain of rice carries enough energy to punch a hole through solid metal. Engineers knew this when they built New Horizons. Before the probe's closest approach to Pluto, mission teams spent months calculating the odds that a small particle in the belt could shatter the entire spacecraft. The math was close enough that some scientists genuinely worried. The probe survived, but Pluto's region is just one small corner of a belt that spans billions of miles. A crewed ship, much larger and slower to maneuver than a probe, would face that same invisible threat for years. And here's the part that changes everything. The faster you need to go to actually reach another star in a reasonable time, the more dangerous every single particle becomes. Speed is both the solution and the problem. The Kuiper belt holds hundreds of millions of objects. Say that slowly. Hundreds of millions. Some are chunks of ice, smaller than a school bus. Some are dwarf planets hundreds of miles across. Most are somewhere in between, frozen lumps of rock and ice tumbling slowly through the dark, far from anything warm, far from anything alive. And here's the strange part. Almost none of them have been seen up close. We've sent exactly one spacecraft close enough to photograph a Kuiper belt object in real detail. New Horizons flew past Pluto in 2015 and captured images that stunned every scientist on the team. Mountains of ice. Plains as smooth as a parking lot. Colors that shifted from pale gray to reddish brown. A world that had been a blurry dot for decades suddenly became real. Then New Horizons kept going and flew past a smaller object, nicknamed Arakoth, in 2019. A contact binary, 2 rounded lobes pressed together like a snowman. It looked like nothing anyone had expected. Red-tinted, ancient, undisturbed for billions of years. 2 objects, out of hundreds of millions. The rest remain unknown. Scientists have catalogued thousands of them, using telescopes, tracking their orbits, guessing at their sizes. But the details, the surfaces, the compositions, the tiny moons some of them carry, all of that stays hidden at this distance. Some of those frozen bodies have moons of their own orbiting them. Scientists confirmed this for several Kuiper belt objects using Earth-based telescopes, tiny worlds orbiting other tiny worlds in the dark, billions of miles from here. The objects in the belt are leftovers. When our solar system formed about 4.5 billion years ago, gas and dust collapsed together. Some of it became the planets. Some of it got swept up by giant worlds like Jupiter and Neptune. But the material in the outermost zone never had enough gravity nearby to pull it all together. So it stayed, frozen in time, orbiting slowly, almost unchanged, since the very beginning. Scientists call these objects some of the most ancient material in the solar system. Studying them is like reading the first page of a book that's 4 billion years old. But reaching them is the problem. Even the closest Kuiper belt objects sit billions of miles away. A signal sent from Earth takes hours to arrive. A spacecraft sent to investigate takes years. And the objects themselves hold almost no heat. Temperatures on their surfaces drop to minus 390 degrees Fahrenheit. Instruments that work fine in a lab tend to behave unpredictably at those temperatures over long periods. One more thing makes these objects unusual. If you stood on the surface of one and looked up at the sky, you would see almost nothing. The other objects in the belt are so far away that none would be visible to the naked eye. just stars, endless stars, and one very faint point of light where our star sits, so dim it would look like nothing more than the brightest star in a very dark sky. Isolated, ancient, and holding secrets scientists haven't unlocked yet. The next object we'll talk about is the most famous piece of this frozen ring, and its demotion caused one of the biggest arguments in modern science. For 76 years, Pluto was the 9th planet. Children learned its name in school. Scientists gave it a number. Textbooks printed its picture alongside Mercury, Venus, and the rest. It had a place in the order of things. Then, in 2006, the International Astronomical Union voted to strip it of that title. Pluto became a dwarf planet. But the science behind the decision tells a story that's actually more interesting than the title it lost. Pluto is not an outlier, sitting alone at the edge of the solar system. It's one of the largest members of the Kuiper belt, a belt containing hundreds of millions of similar frozen objects. It just happened to be discovered first, back in 1930, before anyone knew the belt existed. Astronomers at the time had no reference point. They saw a small distant object and called it a planet because that was the only category available. Pluto is about 1,400 miles across. For comparison, that's roughly the distance from Chicago to Miami. It's smaller than Earth's moon, smaller than 7 other moons in the solar system, and its orbit is tilted and stretched into an oval shape, unlike the near-circular paths of the 8 major planets. When astronomers started finding other Kuiper belt objects in the 1990s and early 2000s, the situation became impossible to ignore. Some of those objects were nearly as large as Pluto. One, called Eris, was actually measured as slightly more massive. If Pluto counted as a planet, then Eris and several others would have to count too. That would push the planet count past 12, maybe higher, with more objects still being found. The scientific community faced a choice: expand the definition of planet to include dozens of frozen Kuiper belt objects, or create a new category. They chose the new category, and the Kuiper belt finally got recognized as the enormous structure it actually is. New Horizons flew past Pluto in 2015 and changed what scientists thought they knew about it. The surface showed active geology, a heart-shaped plain of nitrogen ice, mountains of water ice taller than the Rockies, signs that the interior might still hold liquid water beneath the frozen crust. A world that many dismissed as a cold, dead rock turned out to be genuinely complex. It has 5 moons. Its largest moon, Charon, is so big relative to Pluto that scientists sometimes describe the two as a double system rather than a planet. And its moon, Pluto's demotion, wasn't an insult. It was a correction that forced us to understand the scale of what surrounds us. The Kuiper belt isn't a handful of stray objects. It's a massive population of ancient worlds that we've barely begun to map, and Pluto is sitting in the middle of all of it, doing things scientists are still trying to explain. The spacecraft that revealed all of this launched at a speed no human vehicle had ever matched. How it reached the belt at all is the next story. And the answer involves a trick that engineers have only pulled off a handful of times in history. January 19, 2006. Cape Canaveral, Florida, a rocket carrying a probe the size of a grand piano lifted off the launch pad and began accelerating. Within hours, it had left Earth's orbit entirely. Within days, it had passed the Moon, a trip that took the Apollo astronauts 3 days to complete. New Horizons did it in 9 hours. It launched at 36,000 miles per hour. That's 10 miles every single second, faster than any human-made object had ever left Earth. And it still needed 9 years to reach Pluto. The engineering team at Johns Hopkins Applied Physics Laboratory had spent years designing the mission. They knew the clock was ticking on something unusual. Pluto's orbit carries it through a range of distances from our star, and in the coming decades, its tilted path would carry it farther away and into a region where its thin atmosphere would freeze entirely. The window to study it, in a useful state, was closing. so they needed speed. As much as they could get, the Atlas V rocket provided the initial push, but the real trick came about a year into the flight, when New Horizons made a close pass around Jupiter. Jupiter's massive gravity grabbed the probe and flung it outward like a slingshot. Scientists call this a gravity assist, and it added another 9,000 miles per hour to the spacecraft's speed. This maneuver sounds simple. It isn't. Hitting the correct angle for a gravity assist requires years of planning and math precise enough to account for the positions of planets months and years in advance. Being even slightly off means the slingshot fails or sends the probe in the wrong direction. The team got it right. New Horizons kept accelerating. By the time it reached Pluto in July 2015, it had covered 3 billion miles. It flew past the dwarf planet at 31,000 miles per hour, close enough to capture images, showing features as small as a mile across. Scientists on the ground waited 4.5 hours for each set of signals to arrive, because that's how long light takes to travel that distance. They couldn't steer the probe in real time. They couldn't correct it. Every instruction had been uploaded weeks in advance. The flyby lasted only 1 day, and then New Horizons kept going, heading deeper into the Kuiper belt toward a smaller target, Urukoth, which it reached in early 2019. The mission still runs today. New Horizons continues transmitting data from beyond Pluto's orbit, reporting back on what the outer solar system looks like from the inside. And yet, for all its speed, all its engineering, all its years of travel, this probe could carry no crew. A human being cannot survive 36,000 miles per hour in a vehicle exposed to deep space. No life support system could sustain people for 9 years on that journey with current technology. No food supply, no radiation shielding adequate for that duration, no way to handle a medical emergency. New Horizons was the best we could do, and it still barely scratched the surface of what reaching another star would require. The speed needed to cross the galaxy in a human lifetime would have to be millions of times faster. And the machine we've built to test the very limit of speed runs on a type of engine that can never get us there. Every rocket that has ever left Earth burns fuel, liquid oxygen and liquid hydrogen, kerosene and oxidizer. The chemistry changes depending on the mission, but the principle stays the same. Burn propellant. Push exhaust out the back. Move forward. This is called chemical propulsion. It has carried humans to the moon. It launched every satellite orbiting Earth. It sent every probe we've ever built toward the outer solar system. And it has an absolute speed ceiling that cannot be broken no matter how much fuel you add. Here's why. To go faster, you need more thrust. More thrust means burning more fuel, but fuel has mass. More mass means the rocket needs even more fuel to accelerate that mass. Add more fuel, and the rocket gets heavier. Heavier means more fuel again. This cycle is called the Tsiolkovsky rocket equation, named after a Russian scientist who worked it out in 1903. At some point, the math stops working in your favor. You can't add enough fuel to meaningfully increase speed, because the fuel itself becomes the heaviest part of the vehicle. For a crewed mission to the Kuiper belt and beyond, you'd need a rocket so large it would be physically impossible to launch from Earth's surface. New Horizons got to 36,000 miles per hour. That sounds fast until you do the math for interstellar travel. The nearest star system is about 4 light-years away. At 36,000 miles per hour, reaching it would take over 75,000 years. Nobody is riding that mission. To cross that gap in a human lifetime, say 80 years, a ship would need to travel at roughly 5% of the speed of light. That's about 33 million miles per hour, nearly 1,000 times faster than New Horizons. Chemical rockets cannot get anywhere near that speed. The energy required would be so enormous that burning all the fuel on Earth wouldn't be enough. Scientists confirmed this across multiple studies. Chemical propulsion, for all its achievements, is physically capped at speeds that make interstellar travel measured in decades completely impossible. So what about going faster? Every engineer working on deep space missions asks the same question. Ion drives push spacecraft using electrically charged particles instead of burning fuel. They're far more efficient than chemical rockets. NASA's Dawn mission used ion propulsion to orbit both Vesta and Ceres in the asteroid belt. But ion drives produce very low thrust. Accelerating a large crewed ship with one would take years just to reach useful speeds. And the thrust is so gentle, it would feel like a light breeze pushing a freight train. Nuclear propulsion offers more energy per pound of fuel. Theoretical nuclear pulse designs from the 1960s suggested a spacecraft could reach a fraction of the speed of light, using a series of nuclear explosions to push it forward. Scientists never built one. The political and safety barriers were enormous. Every option beyond chemical rockets remains either unproven at scale, financially impossible, or physically too dangerous to test. So we're left with a ceiling, a hard, math-confirmed ceiling, on the speed of any machine we can currently build. And that ceiling sits thousands of times below what deep space travel actually requires. The problem with that ceiling goes beyond just being slow. At the speeds we'd actually need to travel, the universe throws something at you that no armor has ever been able to stop. Hold a grain of sand between your fingers. Look at it. Feel how light it is. Blow it off your fingertip. Nothing. It weighs almost nothing and carries almost no energy at the speed your breath moves it. Now imagine that same grain hitting a spacecraft moving at 1 million miles per hour. At that speed, a grain of sand carries the energy of a small explosive. Physics confirms this. The kinetic energy of any object grows with the square of its speed. Double the speed, 4 times the energy. 10 times the speed, 100 times the energy. 1 million miles per hour is roughly 30 times faster than New Horizons, and the energy at that speed turns microscopic particles into something closer to a bullet than a speck of dust. Scientists at Johns Hopkins were already worried about this problem during the New Horizons mission, and that probe only moved at 36,000 miles per hour. In the weeks before Pluto's flyby, the mission team ran calculations to figure out whether a sand grain-sized particle in the belt could destroy the spacecraft. The math was close enough to make senior engineers lose sleep. The probe survived, but the concern was real and documented. Now scale that up. To reach the nearest star in under a century, a spacecraft would need to move at several percent of the speed of light. That's millions of miles per hour. At those speeds, a particle smaller than a human red blood cell carries enough energy to punch straight through inches of solid steel. Deep space is full of particles. Interstellar space, the region beyond the Kuiper belt, holds an average of about 1 hydrogen atom per cubic inch of space. That sounds almost empty. And it mostly is. But a ship moving at millions of miles per hour sweeps through enormous volumes of space every second. The atoms and particles it runs into hit the front of the ship with an energy that compounds fast. Think of it like this. Walking through a light rain, you stay mostly dry, run through that same rain at full speed, and you get soaked in seconds. Same rain, different result because of speed. Interstellar dust and gas work exactly the same way. Engineers studying the Breakthrough Starshot project, a real proposal to send a tiny probe toward the nearest star, identified this as one of the central unsolved problems. Even a chip-sized spacecraft would need protection from impacts at those velocities. A human-scale vessel would require shielding so massive it would add weight that current launch systems cannot handle. There's an additional layer to the problem. The particles you'd hit at high speed in the Kuiper belt region are mostly ice. Ice, when struck at hypervelocity, doesn't just bounce. It vaporizes instantly and creates a small plasma burst. That burst of energy can damage electronics and melt surrounding material even if the original particle was invisible to any instrument on board. You'd never see the hit coming. You'd just stop working, and here's the piece that engineers are still fighting over. What material? What thickness? What shape of shield could survive thousands of years of those impacts on a journey to another star, without adding so much weight that the ship can never leave? Nobody has an answer yet, but the problem of dust is only one layer of what the belt throws at you. The next threat isn't physical, it's the speed of light itself, turned into a weapon against communication. Every spacecraft designer faces the same brutal choice: add more shielding, and the ship gets heavier. A heavier ship needs more fuel. More fuel adds more weight. More weight demands even more fuel. The cycle compounds until the vehicle is too massive to launch, too slow to be useful, or both. This is called the mass penalty, and it is one of the central reasons deep space travel to other star systems remains physically out of reach. Here's how bad it gets. New Horizons, the fastest probe ever launched, weighs about 1,000 pounds fully fueled at launch. For a crewed vessel, even the most minimal design carrying a small crew with basic life support, food, water and emergency equipment, you're looking at hundreds of thousands of pounds, probably more. Now add shielding. Current spacecraft designed for the inner solar system use thin metal plates and layered insulating materials that handle slow-speed debris and micrometeorites. That approach works fine for satellites in Earth orbit where particles move at only a few miles per second. The Kuiper Belt region and interstellar space require something fundamentally different. The particles out there aren't just fast, they're crossing enormous distances and arriving at unpredictable angles. A shield thick enough to absorb a hypervelocity impact at millions of miles per hour, the speed you'd need to make interstellar travel work in any reasonable time frame, would need to be built from materials we don't fully understand yet, in thicknesses that haven't been tested. Some researchers proposed using a hydrogen cloud ahead of the ship, a bow of gas that slows incoming particles before they hit the hull. Others suggested a magnetic field generator that deflects charged particles the way Earth's magnetic field deflects solar wind. Both ideas work on paper to some degree. Neither has been tested at scale. Neither team has solved the weight and power requirements those systems demand. The materials science problem is even harder than the engineering one. At extremely high impact speeds, almost no known material absorbs energy well. Most materials shatter, crack, or vaporize on impact. Even graphite composites and titanium alloys, two of the toughest materials we use in aerospace, fail in ways that become unpredictable at velocities higher than those tested in any laboratory. One proposal suggested shaping the front of the ship like a sharp cone to deflect impacts rather than absorb them, similar to the way a ship's hull is shaped to push water aside. The math supports the idea, but the cone would still take enormous abuse over a multi-decade journey, and no material currently rated for spacecraft use has been tested for that combination of cold, radiation, and repeated high-speed impact over years. The shielding problem isn't just unsolved, it might not have a practical solution with materials that exist today. And even if engineers cracked the shielding question completely, a different problem would still be waiting. One that no material can fix. When a spacecraft is 4 billion miles away and something goes wrong, there's a delay before anyone on Earth even knows about it. And by the time a response arrives, whatever happened has long since played out. Every signal ever sent to a spacecraft travels at the speed of light. Radio waves, like all electromagnetic signals, move at 186,000 miles per second. That's the fastest anything in the known universe can travel. Engineers beam commands to spacecraft using massive dish antennas that belong to NASA's Deep Space Network, and those signals race outward at the absolute physical limit of speed. And they still take hours to arrive. When New Horizons was near the inner edge of the Kuiper Belt, a signal sent from Earth took more than 4 hours to reach the probe. A response from the probe took another 4 hours to travel back. Total round trip for a single exchange, over 8 hours. Think about what that means in practice. Imagine a spacecraft is heading toward a large object. A sensor detects the object. It sends a warning to Earth. Mission controllers receive the warning 4 hours later. They send a course correction command. That command travels 4 hours back. By the time the spacecraft receives the instruction to change direction, 8 hours have passed since the problem was first detected. In space, 8 hours of travel at tens of thousands of miles per hour covers an enormous distance. Whatever was in the path is long past. The correction either happened automatically or it didn't happen at all. This is why every deep space mission operates almost entirely on pre-programmed instructions. Mission controllers cannot steer these vehicles in real time. Every decision, every sequence of actions, every response to a possible emergency has to be anticipated and coded into the spacecraft's computer months or years before the event happens. For robotic probes, this is difficult but manageable. Scientists are careful. They plan meticulously. They build in as many automated responses as they can. For a human crew, the picture changes completely. Equipment breaks in unexpected ways. A crew member makes a mistake or faces a medical emergency that no pre-programmed checklist covers. On the International Space Station, which orbits only 250 miles above Earth, emergency support can arrive or coordinate in near real time. Communication delay is under a second. At Kuiper belt distances, a crew facing a crisis would receive no real-time guidance. Every decision would fall entirely on the people aboard the vessel. Every problem would have to be solved with whatever equipment and knowledge they brought along. No expert consultation, no second opinion from a specialist. Just the crew, the ship, and whatever is going wrong. The radio delay also affects navigation. Course corrections in deep space can't be checked and double-checked in real time. An error in trajectory that a controller spots on Earth takes hours to communicate, and hours more for the spacecraft to confirm it received and executed the correction. Tiny navigation errors accumulate. New Horizons required a precise correction of 128 miles per hour during its journey to ensure a safe flyby of Pluto. That correction had to be calculated, transmitted, received, and confirmed across billions of miles, with no room for a live conversation. Engineers pulled it off, barely, and the pressure involved in managing a crewed mission under those same constraints is almost impossible to imagine. The delay is a hard limit. The speed of light cannot be increased, and for any crew heading toward the outer solar system, that delay grows longer with every mile they travel. But there's a second problem hiding behind the communication barrier, one that gets even worse the farther out you go. In the fall of 2015, a team at the Johns Hopkins Applied Physics Laboratory faced a problem most people will never encounter. They needed to adjust the speed of a spacecraft traveling at 31,000 miles per hour, roughly 3 billion miles from Earth, using only math and radio waves. And they had one shot to get it right. New Horizons was on its way from Pluto toward a smaller Kuiper belt object, Arrokoth, and the trajectory needed to be precise. The spacecraft had to pass within a very specific window of space near its target, close enough to gather scientific data, but safe from any debris or unexpected hazards in the area. The team calculated the required correction down to fractions of a second. The probe would fire its thrusters at exactly the right moment, for exactly the right duration, to shift its course by the needed amount. The result was a velocity change of 128 miles per hour. 128 miles per hour, executed by a machine the size of a grand piano traveling faster than a bullet, 3 billion miles away. The command was transmitted from the Deep Space Network's massive antenna dishes. It raced outward at the speed of light and took hours to reach the probe. The team then waited hours more for a confirmation signal to come back. The correction worked. New Horizons adjusted its path and continued toward Arrokoth. But this story reveals how extreme the challenges of deep space navigation actually are. On Earth, if you're driving and realize you need to turn, you turn. Instant response. If you're flying a plane, communication between pilot and air traffic control happens in seconds. Any error gets caught and corrected fast. Deep space removes all of that. The probe had no ability to call back and ask for clarification. The team on Earth had no ability to ask the probe what it was sensing in the moment. Every piece of the correction had to be worked out in advance, transmitted, as a set of precise instructions and trusted to execute correctly without supervision. If the math had been slightly wrong, the spacecraft might have flown past its target too far to gather useful data, or encountered an undetected hazard, or fired its thrusters at the wrong angle and sent itself drifting into an uncorrectable trajectory. The margin for error over billions of miles is nearly zero. Now consider what this means for a crewed mission. A human ship in the Kuiper belt would face the same navigation demands. Every course correction would require the same lead time, the same perfect math, the same blind trust that the command executed correctly. But a crewed ship carries people whose lives depend on each decision. And the ship itself, far larger than a probe, carries more variables that can go wrong. Astronauts on the International Space Station can look out a window and visually confirm their orientation. Teams on the ground can see real-time data streams. Corrections happen in minutes. In the Kuiper belt, correction takes hours to request and hours more to confirm. A mistake at that distance, with a crew aboard, would be a different kind of problem entirely. And navigation isn't the only challenge waiting in that frozen dark. The temperature out there does something to materials and machines that engineers still haven't fully solved. The Kuiper belt operates at minus 390 degrees Fahrenheit. Take a second with that number. Water freezes at 32 degrees. Your freezer sits around 0 degrees. The coldest temperature ever recorded on Earth's surface was about minus 129 degrees Fahrenheit in Antarctica. Minus 390 degrees is more than 3 times colder than the most extreme cold ever recorded on this planet. At that temperature, things behave differently. Gases that normally float as invisible vapors freeze solid. Certain metals become brittle instead of flexible. Rubber seals, which keep spacecraft joints airtight, crack and fail. Lubricants that keep mechanical parts moving smoothly solidify into rigid masses that jam up whatever they were protecting. This is confirmed across decades of engineering experience. Materials that survive just fine in Earth's cold winters or in near-Earth orbit begin to fail in predictable and sometimes catastrophic ways when exposed to deep space temperatures for long enough. The Voyager probes, launched in 1977, demonstrated that electronics can survive for decades in these conditions. Both Voyager probes are still functioning, still transmitting data from beyond the outer solar system, so the cold alone doesn't automatically destroy a machine. But there's a difference between surviving the cold and surviving the cold for the duration required by a crewed mission. Voyager's designers built their systems to last as long as possible. They used heaters powered by onboard nuclear generators to keep critical components warm enough to function. Those generators use the radioactive decay of plutonium to produce heat, which is then converted into electricity. Slowly, over decades, the generators weaken. Voyager 1's power output has dropped significantly since launch, and mission controllers have been carefully shutting down non-essential systems to preserve what remains. A crewed ship heading through the Kuiper belt would need sustained heating for the entire journey. The crew quarters, water systems, food storage, medical equipment, and hundreds of other life-critical systems all require temperatures that would feel laughably warm by Kuiper belt standards. Maintaining that heat would require enormous amounts of power. In the inner solar system, solar panels can gather enough energy to power a spacecraft. Past Jupiter, sunlight becomes too weak to be useful. A large crewed vessel in the Kuiper belt would need nuclear power, likely multiple reactors, running continuously for years. And nuclear reactors add weight. More weight means more fuel to launch. More fuel means more weight again. The cycle that makes every deep space challenge harder connects back to itself. The cold also creates a risk that no engineer can fully calculate in advance. After years of extreme cold cycling, materials develop microscopic cracks, seams stress, welded joints weaken. A spacecraft designed to hold pressure for a crew over a decade of deep cold is an engineering problem that has never been fully solved, because no crew has ever been sent that far. the temperature is survivable in theory, but solving it in practice for the duration and scale a crewed Kuiper Belt mission would demand requires breakthroughs that haven't happened yet. And the cold isn't even the most hidden danger. Out in the belt, something else is silently pulling at spacecraft without making a sound. Past Jupiter, the solar panels go dark. At Earth's distance from our star, sunlight delivers enough energy to power a spacecraft's systems. The International Space Station uses enormous solar panels, spanning over 300 feet, to run everything on board. Satellites in orbit around Earth or Mars do the same. Solar power works well in the inner solar system, but energy from our star weakens with distance following a precise mathematical rule. Double the distance from the source, and the available energy drops to 1/4 of what it was. By the time you reach Jupiter, solar power has already fallen to about 4% of what it provides at Earth's distance. Out in the Kuiper Belt, billions of miles farther, sunlight drops to less than 1% of its strength at Earth. Solar panels at that distance would need to be the size of several city blocks just to gather enough energy to keep a small probe's heaters running. A crewed ship would need something far more powerful. Nuclear power is the confirmed solution for deep space missions. The technology already exists in small form. Both Voyager probes use radioisotope thermoelectric generators, devices that produce electricity from the heat of decaying radioactive material. New Horizons uses one as well. The Cassini mission that orbited Saturn used the same technology. These generators work by allowing a radioactive element, in most cases plutonium-238, to decay naturally and release heat. That heat gets converted into electricity through a process similar to how a car alternator works, but without moving parts. The generators are sealed, compact, and incredibly reliable. Voyager 1's generator has been running continuously for almost 50 years. For a small probe, one generator produces enough power to run the essential systems. For a crewed ship, you'd need dramatically more power. Life support, heating, computing, propulsion, communications, medical systems. All of it draws electricity constantly. Small generators couldn't handle the load. That points toward full nuclear reactors, not just decay-based generators. Reactors can produce far more power by controlling a nuclear fission reaction, splitting atoms to release large amounts of heat. The heat drives turbines that generate electricity, similar to how a coal or gas power plant works. The challenge is weight and safety. A nuclear reactor large enough to power a crewed deep space vessel would be heavy, very heavy. Combining that with the fuel, shielding, crew habitat, life support, and all the other requirements of a crewed mission pushes the total mass of the vehicle into ranges that make launching from Earth's surface almost impossible with current rockets. Safety is a second problem. A reactor launch failure that scatters radioactive material over a populated area is a political and environmental disaster. Every nuclear-powered probe ever launched by the United States went through extensive safety reviews and used fuel forms designed to survive a launch accident without releasing harmful material. Scaling to a crewed reactor mission requires solving these problems at a level that has never been attempted. No crewed spacecraft has ever flown with a full nuclear reactor. The power is available in theory. The engineering to make it safe, light, and launchable remains an open problem. And while engineers wrestle with the power question, something else is quietly operating in the belt that could redirect a ship without anyone knowing it had happened. Space looks empty. It isn't. The Kuiper Belt holds hundreds of millions of objects. Scientists have catalogued thousands of them with enough precision to map their orbits, but the total count of objects smaller than 60 miles across remains genuinely uncertain. That uncertainty matters for navigation. Every object with mass generates gravity. The effect from any single small Kuiper Belt object on a passing spacecraft is tiny, far too small to measure directly with instruments aboard the vessel. But gravity acts continuously, over days, weeks, and months, a series of tiny gravitational nudges from unseen objects can add up and shift a spacecraft's path by a meaningful amount. Engineers confirmed this effect during the New Horizons mission. The probe's trajectory was tracked obsessively throughout its journey, and small corrections were required that were not fully predicted before launch. Some of those corrections came from gravitational influences that models had underestimated. For a crewed mission traveling for years through the belt, the accumulated gravitational drift from undiscovered objects could send a ship off its planned route without any single dramatic event. No collision, no alarm, just a slow, invisible curve in the path, discovered only when the ship checks its position and finds it's no longer where it expected to be. Ground-based course corrections handle this for unmanned probes. Engineers detect the drift, calculate the fix, send a command, and wait hours for confirmation. The process is tedious but workable. For a crewed ship operating at the communications range of the Kuiper belt, the same drift would require the crew itself to detect and correct the problem. They'd need instruments precise enough to measure tiny changes in trajectory. They'd need the computing power to calculate the correct thruster burn. And they'd need enough fuel reserves to make the correction after years of travel had already burned through most of what they launched with. Fuel reserves become critical here. A ship that launches with exactly enough fuel for its planned route has no margin for unexpected corrections. A ship that launches with extra fuel for corrections is heavier from the start, which requires even more fuel to launch, which adds more weight, and the cycle returns to the same brutal arithmetic every deep space mission faces. There's another layer. Some researchers believe the gravitational patterns of Kuiper belt objects near the outer edge show signs of influence from a large, undiscovered body in the far outer solar system. An object large enough to be reshaping the orbits of distant Kuiper belt objects would be powerful enough to subtly alter the path of a passing spacecraft too. The name given to this theoretical object is Planet 9. No telescope has confirmed its existence. No mission has been planned to search for it directly, but the orbital data from dozens of outer solar system objects continues to suggest that something large is out there, pulling on them in ways that nothing in our current maps can explain. If Planet 9 exists, any navigation plan for deep space travel would need to account for it. A gravitational pull that nobody mapped, from a planet nobody has seen, affecting a ship nobody has built. The Kuiper belt keeps its secrets carefully. Something is out there. Scientists haven't seen it. No telescope has captured a direct image. No probe has flown anywhere near it. But the mathematical evidence that something large exists in the far outer solar system has been building for years. It started with a pattern. Astronomers studying the orbits of small, distant objects beyond the main Kuiper belt noticed something unexpected. A cluster of these objects had their orbits tilted and stretched in a way that pointed toward the same region of sky. The odds of that happening by random chance were calculated at roughly 1 in 10,000. Researchers Konstantin Batygin and Michael Brown published a paper in 2016 proposing an explanation. They argued that a large, undiscovered planet in the far outer solar system was gravitationally herding those objects, pulling their orbits into alignment. The hypothetical planet got nicknamed Planet 9. Based on the orbital data, scientists estimated it could be 5 to 10 times the mass of Earth, orbiting our star at a distance of roughly 400 to 800 astronomical units. For reference, 1 astronomical unit is the distance from Earth to our star, about 93 million miles. 400 times that. The object, if real, would sit almost impossibly far from anything we've ever visited. At that distance, even a planet several times Earth's size would reflect almost no light toward us. Finding it requires either extraordinary luck, pointing a telescope at exactly the right patch of sky at exactly the right time, or systematic scanning of enormous areas of dark space. Teams have been searching the Vera C. Rubin Observatory in Chile, designed to survey the entire visible sky repeatedly, was partly expected to find Planet 9 or rule out its existence once it reached full operation. As of current data, no confirmed detection has been made. The debate within the astronomical community is active and unresolved. Some researchers argue that the orbital clustering that started the hypothesis is a statistical artifact, a result of observational bias, rather than a real gravitational signal. Others maintain that the pattern is too consistent to dismiss. What's confirmed is this: the outer Kuiper belt contains real orbital anomalies that current models don't fully explain. For anyone planning a deep space mission, the debate matters practically. A planet with 5 to 10 Earth masses, sitting at 400 or more astronomical units, generates a gravitational field strong enough to shift the trajectories of anything passing through that region of space. Planning a route through the outer solar system without knowing whether Planet 9 exists, where it sits, or how strong its gravitational pull runs in each direction is like charting a sea voyage without knowing whether a large island sits in the middle of your route. You might sail past it without incident, or it might send you hundreds of miles off course. The uncertainty is uncomfortable for mission planners, and it remains unresolved. Meanwhile, the probes that have already crossed the Kuiper Belt region, the ones we actually launched and tracked for decades, taught scientists lessons that no theoretical model had predicted. And the most important lesson from those missions wasn't about speed, or temperature, or distance. It was about what happens to a machine when you push it beyond everything engineers had ever designed. In 1977, 2 spacecraft launched within weeks of each other. Both were built to last 5 years. Neither engineer on the project expected them to still be transmitting data nearly 50 years later. Voyager 1 and Voyager 2 were designed to take advantage of a rare planetary alignment that allowed a single spacecraft to visit multiple outer planets using gravity assists. The alignment only happens once every 175 years. Scientists pushed for the missions knowing the window was closing. Voyager 1 flew past Jupiter and Saturn. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune. Both used the gravitational pull of each planet to accelerate towards the next. By the time they finished their planetary tours, they were moving fast enough to leave the solar system entirely. Both probes crossed through the outer solar system, through the Kuiper Belt region, and eventually into interstellar space. Voyager 1 became the first human-made object confirmed to have left the solar system and entered true interstellar space in 2012. Here's what they found along the way. The outer solar system and Kuiper Belt region are full of charged particles streaming from our star, a flow called the solar wind. Voyager instruments measured this particle flow as the probes moved outward. At a certain point, the solar wind slowed dramatically, piling up where it met the thin resistance of interstellar space. Scientists called this boundary the heliopause. Crossing that boundary taught researchers something important. Interstellar space contains its own particle environment, denser in some directions than models had predicted. The radiation environment outside the heliopause is different from what exists inside. Cosmic rays, high-energy particles from distant supernovas and other violent events across the galaxy, penetrate far more deeply into interstellar space than they penetrate the inner solar system. For a crewed mission, this matters enormously. A crew heading outward through the Kuiper Belt and beyond would leave the protective bubble of our star's magnetic influence. Cosmic ray exposure would increase significantly. Over years of travel, that radiation load would damage DNA and raise cancer risk. The Voyager probes also demonstrated something engineers hadn't fully predicted: how deeply the extreme cold and long duration of operation stressed their systems. Instruments failed. Backup systems that had never needed to activate kicked on. Certain electronic components drifted in their calibrations and required retuning from Earth. None of these failures were catastrophic for robotic probes, but for a crewed mission, each one of those surprises represents a life-threatening event waiting to unfold. What the Voyager data confirmed most clearly is that our models of the outer solar system were incomplete. The real environment differed from the simulations in ways that mattered for engineering. The heliopause wasn't where models placed it. The particle density in interstellar space varied from predictions. The magnetic field orientation was unexpected. Every correction we now make to those models came from real data that the probes sent back at the edge of their functional limits. What they couldn't tell us is what a human body endures over decades in that environment. No instrument measures bone density loss. No sensor reports psychological breakdown from years of isolation. No telemetry captures the effect of watching everything familiar shrink to a point of light and vanish. The Voyager probes showed us the door, but they couldn't tell us what it costs to walk through it. Here's the thing almost no one expects. The Kuiper belt, this enormous ring of hundreds of millions of objects, spanning billions of miles, contains less total mass than you might think. Current estimates place the total mass of the Kuiper belt at somewhere around 4 to 10% of Earth's total mass. 4% of Earth, spread across a donut-shaped ring that spans from 2 to 4.5 billion miles from our star. Most people assume that a region this large, holding this many objects, must be heavy. The logic seems sound. More objects, more mass. But scale ruins intuition here. Think of it this way. Pour a handful of glitter into a swimming pool. The swimming pool is enormous. The glitter contains hundreds of thousands of individual pieces. But the total weight of the glitter barely registers compared to the water. Now replace the swimming pool with a ring the size of the solar system and replace the glitter with frozen rocks. And you're starting to get a picture of the Kuiper belt's actual density. The asteroid belt between Mars and Jupiter holds even less mass than the Kuiper belt. The entire asteroid belt combined weighs less than 4% of our moon. For something that movies treat as a dangerous field of massive boulders, the asteroid belt is almost laughably sparse. How did the Kuiper belt end up with so little mass for its size? The answer goes back to the early solar system. When the planets were forming about 4.5 billion years ago, Neptune and Uranus went through a period of orbital instability. Their paths shifted. As Neptune moved outward to its current position, its gravity scattered enormous amounts of material that had been accumulating in the outer solar system. Material that could have clumped into another full planet got flung outward, inward, or ejected from the solar system entirely. What remained in the Kuiper belt region is the leftover material that survived those interactions, a tiny fraction of what was originally there. The low total mass of the belt also explains why no planet formed there. A region needs enough material to gather itself together through gravity. The Kuiper belt region didn't have enough density for that process to complete. The objects out there are too spread out, too slow relative to each other, and too small to pull themselves into a single world. This also means the belt is stable. Most objects in the Kuiper belt stay in nearly the same orbits for billions of years, barely changing their paths. The chaos that movies portray doesn't exist. The belt sits frozen not just in temperature, but in time, almost unchanged since the solar system's earliest period. Scientists call this a pristine environment. Studying these objects gives a view into conditions that existed before Earth formed. The ice and rock in the belt holds the same chemical makeup it had 4 billion years ago. The low mass surprised researchers when they first estimated it. Models had predicted the belt should hold much more material. The gap between predicted and actual mass remains one of the open puzzles of solar system science. Something removed that mass long ago. The leading theory points to Neptune, but the exact sequence of events, the precise timing, the full picture of what happened in those first few 100 million years, remains incomplete. The belt survived, but the real mass it once held vanished into the dark long before humans existed to look for it. 4.5 billion years ago, our solar system was a spinning cloud of gas and dust. No planets, no moons, no frozen rings, just a massive, slowly rotating disk of raw material pulled together by gravity around a new hot center. Over millions of years, pieces of that disk began sticking together. Dust grains collided and clumped. Clumps grew into pebbles. Pebbles became boulders. Boulders merged into larger bodies. The inner disk, where temperatures were higher, formed rocky planets. The outer disk, where the cold allowed ice to exist, formed a different kind of world. In the outermost zone of that early disk, gravity was weaker, material was more spread out, objects formed more slowly and never gathered enough mass to build a full planet. Instead, they froze in place. Literally, the water, ammonia, and methane that make up much of their bulk turned to ice almost immediately at those distances from the forming star. What you find in the Kuiper belt today are those same frozen objects, almost unchanged. Scientists call this material primordial. It has never been heated by a nearby star, never been crushed by the pressure of a larger world's interior, never been transformed by geology. It is as close to the raw ingredients of our solar system as anything we can currently study. When New Horizons photographed Arrokoth, the contact binary object it reached after Pluto, researchers got their first close look at one of these ancient builders. Arrokoth's two lobes formed separately from the same local cloud of material and then slowly drifted together under their mutual gravity, joining gently rather than smashing. That gentle merging suggested the early outer solar system was calmer in some regions than scientists expected. The surface of Arrokoth showed a reddish color caused by organic molecules, called tholins, compounds that form when simple chemicals like methane and nitrogen ice are hit by cosmic radiation over billions of years. The same reddish compounds appear on other Kuiper belt objects and on the moons of outer planets. Here's what makes this remarkable. Those organic molecules, the chemical ancestors of compounds found in living cells, formed naturally in the frozen dark of deep space. Scientists don't claim life exists in the belt, but the chemistry happening on those surfaces is the same basic chemistry that under different conditions produces the building blocks of life. The Kuiper belt is essentially a deep freeze of the raw materials that built everything in our solar system. The water on Earth likely came partly from icy objects that migrated inward during the early solar system's chaotic period. The belt still holds massive amounts of that same ice, sitting undisturbed for billions of years. For planetary scientists, the belt is priceless. For mission planners, it's a nightmare. The same conditions that preserve these objects in pristine scientific condition, the extreme cold, the distance, the lack of any nearby heat source, make them almost impossible to study up close. Reaching one requires years of travel. Staying near one to conduct a full study would require sustaining a spacecraft or crew in one of the most hostile environments in the solar system. Every sample scientists wish they could collect sits locked behind billions of miles of frozen dark, and it formed from the exact same ingredients that eventually, over billions of years, became you. Close your eyes and try to picture it. You are standing on a surface of dark, reddish ice. The ground beneath your boots barely registers gravity. You weigh almost nothing out here. A small jump would send you floating upward for several seconds before you drifted back down in slow motion. The object you're standing on might be 30 miles across, 50 miles, maybe 100, but its gravity is so weak that a running leap could potentially launch you off the surface entirely. The sky above you is black, completely, absolutely black in every direction. There is no atmosphere to scatter light, no dust to create a horizon glow, no clouds, just stars, sharp and motionless. More stars than you'd ever see from Earth, because there's nothing to blur them. Look for our star. It's there, but you'd need to know exactly where to look. From the inner edge of the Kuiper belt, our star appears as the brightest object in the sky, but dim enough that it casts almost no warmth. No tan, no squinting, just a hard white point of light, slightly brighter than the other stars around it, and cold. Look for other Kuiper belt objects. You won't see any. The objects nearest to you are millions of miles away. The belt looks dense on a solar system map, because the map shows billions of miles compressed into a small image. From the inside, standing on one of those objects, you'd see nothing but empty sky. Scientists confirmed that the spacing between objects is too vast for any neighboring body to appear visible to the naked eye. The silence would be total. Sound requires air. There is none. Whatever is happening to the surface around you, chemical reactions driven by cosmic radiation slowly breaking apart and reforming the ice, happens in complete and permanent silence. The temperature would kill you in seconds without a suit. -390 degrees Fahrenheit. Every exposed surface cools toward that number with nothing to stop the process. Your suit would need active heating powered by a nuclear source because there's no sunlight out here worth capturing. If you carried a radio and tried to call someone on Earth, your voice would travel at the speed of light for over 4 hours before anyone heard it, and you'd wait another 4 hours for a response. A real-time conversation is physically impossible. The darkness around you isn't the dramatic darkness of a movie space scene. It's something slower and more total than that. The kind of dark that has existed here, unbroken, for 4 billion years. The kind of dark that makes the distances between stars feel personal. Looking outward from the belt's edge, you'd be staring into the gulf between solar systems. The nearest star, Proxima Centauri, sits about 4 light-years away. At that distance, it appears as a faint reddish dot among the stars. To reach it at the fastest speed any human machine has ever achieved, you'd need over 75,000 years. Standing on that frozen surface, looking at that faint red dot, you'd understand the Kuiper belt's role in a way no textbook can deliver. It isn't just the edge of our solar system. It's the beginning of a distance so vast that it makes everything we've built look like a message in a bottle dropped into an ocean with no shore. In 2016, a group of physicists and engineers announced a proposal that most people dismissed as fantasy. They wanted to send a spacecraft to the nearest star system, Proxima Centauri, in 20 years. For comparison, New Horizons, the fastest probe ever launched, would take over 75,000 years to cover the same distance. 20 years sounds impossible. So how did the team claim it could work? By making the spacecraft almost weightless. The breakthrough Starshot project, backed by scientist Stephen Hawking and tech investor Yuri Milner, proposed a radically different approach to space travel. Instead of a large, heavy vehicle carrying fuel and instruments and shielding, they proposed a spacecraft the size of a postage stamp. A chip, a few grams of mass, carrying a camera, a transmitter, and a thin sail made of reflective material. The plan was to accelerate this chip using light. Physicists confirmed that light carries momentum. It exerts a tiny physical pressure on whatever it strikes. In everyday life, this pressure is too small to matter. But in space, with no friction and no air resistance, even a gentle push applied consistently can accelerate a lightweight object to remarkable speeds. The Starshot proposal called for building a ground-based laser array capable of producing an enormous beam of focused light. This beam would strike the reflective sail of the chip-sized spacecraft and push it. The acceleration would last only a few minutes, during which the probe would gain speed continuously. The target velocity was 20% of the speed of light, about 37 million miles per hour. At that speed, the chip would cross the 4 light-years to Proxima Centauri in roughly 20 years. The concept is physically valid. Scientists confirm that light sails work. Several test missions have already demonstrated the basic principle in Earth orbit. The Japan Aerospace Exploration Agency flew a small light sailcraft called Icaros past Venus in 2010 and confirmed it could be steered using solar light pressure. But the Starshot laser would need to be orders of magnitude more powerful than anything humans have built. The energy required to push even a gram-scale probe to 20% of light speed using a laser would consume an amount of electrical power comparable to the total output of a large power plant running for several minutes. The laser array itself would need to be enormous, possibly covering kilometers of land, and perfectly coordinated. The chip would also need to survive the journey. 20 years of exposure to cosmic radiation, microparticle impacts at relativistic speeds, and the vacuum of interstellar space. Engineers have proposed a protective coating for the leading edge of the sail, but testing any material against impacts at those speeds is currently beyond the capability of any existing laboratory. And when the chip arrives at Proxima Centauri, it cannot slow down. The laser stays behind on Earth. There's no mechanism to brake. The probe would fly through the target star system in a matter of hours, capture whatever data it could, and then continue outward into deep space. Everything about this mission is at the absolute edge of what physics allows, and it only works for something the mass of a paperclip. The Starshot chip weighs a few grams. A crewed spacecraft capable of keeping humans alive for a 20-year journey would weigh hundreds of thousands of pounds, possibly millions. The difference between those two numbers is the reason interstellar human travel remains out of reach for the foreseeable future. Scale matters brutally in physics, and the laser required to push a chip to 20% of the speed of light already strains the limits of what human engineering can build. Here's the math in simple terms. Kinetic energy, the energy of motion, scales with mass. Double the mass and you need double the energy to reach the same speed. But the mass difference between a gram-scale probe and a crewed ship isn't a factor of 2. It's a factor of several hundred million. To accelerate a crewed ship to even 10% of the speed of light using the same laser sail approach, the energy required would be roughly equivalent to the total electrical output of the entire United States running continuously for years. The laser array needed to deliver that energy would need to be larger than any structure humans have ever built, and it would need to fire with a precision and consistency that no current engineering can achieve. The sail itself would also be a problem. A gram-scale sail can be made thin enough to have almost no mass, while still being large enough to catch the laser's beam. A sail large enough to push a crewed ship would be so massive that the mass of the sail itself becomes a significant fraction of what needs to be accelerated. The efficiency collapses. There's also the question of brewing. A chip-sized probe that can't slow down loses almost nothing by flying through a star system in hours. A human crew that can't slow down faces a different problem entirely. They'd fly past their destination at 20% of the speed of light and continue outward into interstellar space forever. To stop, the ship needs a braking system. Any braking system adds mass. More mass requires more energy to accelerate. The cycle returns. Some theoretical proposals suggest using the magnetic field of the target star system to slow the ship gradually. Others propose carrying a second, smaller laser array that deploys ahead of the ship and fires backwards to decelerate. Each proposal adds complexity, mass, and new engineering problems that haven't been solved. The fundamental barrier isn't imagination. Engineers and physicists have produced brilliant proposals. The barrier is energy and mass. Our current ability to generate and focus the energy required sits many orders of magnitude below what these missions would demand. One more factor nobody advertises loudly: relativity. At 20% of the speed of light, relativistic effects begin to appear. Time aboard the ship passes slightly slower than time on Earth. For a 20-year journey at that speed, the difference is small, only a few months. But at higher percentages of light speed, the effect becomes dramatic. A crew traveling at 90% of light speed would age only a fraction of the time that passes on Earth. Physics keeps moving the goalpost every time engineers think they found a workaround. At low speeds, interstellar dust is harmless. At high speeds, it becomes one of the most dangerous materials in the universe. This is the physics of relativistic impact, and it's a problem every serious deep space mission proposal has to address. Interstellar space contains an average of roughly 1 hydrogen atom per cubic centimeter. That's about the size of a sugar cube. 1 atom. Sounds almost perfectly empty. And at the speeds of current spacecraft it is. New Horizons moves through that environment with zero meaningful impact from individual particles. Now change the speed. Push a spacecraft to 10% of the speed of light, roughly 19 million miles per hour, At that velocity, the ship sweeps through an enormous volume of space every second. Each hydrogen atom it hits carries far more energy in the ship's reference frame than it would at rest. The particle doesn't move faster, the ship does, and from the ship's point of view, each particle is hitting it at 10% of the speed of light. At that impact speed, a single hydrogen atom doesn't cause measurable damage, but the ship hits billions upon billions of them every second. Cumulatively, the effect is real and confirmed. For larger particles, the situation becomes critical. Interstellar space also contains microscopic grains of dust, tiny fragments of carbon, silica, and ice ranging from fractions of a micron to a few microns across. At 10% of the speed of light, a single micrometer-sized dust grain carries enough energy on impact to release a burst equivalent to a small explosive charge. The front surface of the ship would experience constant bombardment. Over years of travel, the leading edge of any vessel would erode. Metal would ablate. Composite materials would pit and crack. Even a beautifully engineered shield would thin out over time, as layer after layer absorbed impacts and was slowly destroyed. Scientists working on the Starshot project calculated that even their gram-scale chip would need its leading edge protected by a specially designed material capable of surviving this erosion for the duration of the journey. The best candidate identified so far is a thin layer of beryllium, which is hard, light, and resists ablation better than most materials at hypervelocity impacts. For a human-scale ship, the erosion problem multiplies. A larger frontal area catches more particles, more impacts per second, more erosion per year. The ship would need a leading shield that starts thick enough to absorb decades of relativistic particle impacts without failing. That shield adds mass. Mass adds to the energy needed to accelerate the ship. The cycle repeats. There's an additional layer that's less obvious. At high velocities, the hydrogen and helium atoms the ship moves through act collectively as a form of radiation. Scientists call this the ram pressure effect, and it has been confirmed mathematically. A ship moving through even low-density interstellar gas at a significant fraction of the speed of light experiences a constant energy flux against its hull that generates heat and transfers energy into the ship's structure. Managing that energy, keeping it from cooking the hull or the crew, requires active cooling systems that run continuously throughout the journey. Speed is the only way to reach another star in a human lifetime, and speed is exactly what makes the journey lethal. Every proposed solution to this problem sits somewhere between unproven and unknown. Every probe we've sent to the outer solar system used a trick. Instead of burning more fuel to go faster, mission engineers used the gravity of planets already moving through space. A spacecraft flying close to a planet gets pulled into that planet's gravitational field. As it swings around the planet and out the other side, it picks up a fraction of that planet's orbital speed and launches forward faster than it arrived. This is a gravity assist, sometimes called a slingshot maneuver. No fuel burned, speed gained for free. It sounds like a perfect solution. The outer planets are enormous. Jupiter alone is 318 times the mass of Earth. Its gravitational pull is immense. A spacecraft swinging around Jupiter can gain thousands of miles per hour in a single pass. New Horizons used Jupiter's gravity assist to add about 9,000 miles per hour to its speed. Voyager 2 used gravity assists from Jupiter, Saturn, Uranus, and Neptune in sequence, each one accelerating the probe further, like a relay of slingshots. So why not use more gravity assists? Why not chain together a dozen of them and get a probe to a significant fraction of the speed of light? The math closes the door on that idea quickly. A gravity assist can only give a spacecraft a fraction of the planet's own orbital speed. The planet's speed is determined by its distance from our star and doesn't change based on how many times a probe flies past it. Jupiter orbits at about 8 miles per second. Even a perfectly executed gravity assist extracts only a portion of that. And once the probe moves faster than the planet itself, it can no longer use that planet's gravity for additional acceleration. Stringing together multiple assists helps, but the cumulative speed you can reach is still a tiny fraction of what interstellar travel demands. The fastest speed achievable through gravity assists alone, using every planet in the solar system optimally, lands somewhere around 150,000 miles per hour. That sounds impressive until you compare it to the 33 million miles per hour needed to cross to the nearest star in a human lifetime. Gravity assists get you to roughly half of 1% of the speed you'd need. Researchers have proposed a more extreme version called a solar gravity assist, where a spacecraft dives close to our star using its immense gravity to slingshot outward at much higher speed. By dipping as close as possible and firing a rocket engine at the closest point, where gravitational energy is highest, a probe could theoretically reach speeds several times higher than anything achieved so far. The problem is the heat. Getting close enough to our star to make that maneuver useful would expose a spacecraft to temperatures that vaporize most materials. Only the Parker Solar Probe, designed specifically for close solar approaches, has survived near star temperatures, and it reached only about 400,000 miles per hour, doing so, still far below interstellar requirements. Gravity assists are one of the greatest tricks in the history of spaceflight. They've sent probes to every outer planet. They've pushed machines to the edge of the solar system. But the physics of how planets move sets a hard ceiling on what they can provide, and that ceiling sits far below the speed that deep space demands. The energy needed for real interstellar travel has to come from somewhere else entirely. The numbers are almost too large to write. To send a crewed ship to the nearest star in under a century, traveling at roughly 5% of the speed of light, the energy required is staggering. Scientists have done the math, and the answer is confirmed. The total energy needed exceeds anything humanity currently produces by an enormous margin. Here's how to picture it. The United States generates roughly 4 trillion kilowatt-hours of electricity per year. That powers every home, every factory, every data center, every electric vehicle in the country for a full year. It's an almost incomprehensible amount of energy for everyday life. To accelerate a crewed ship of modest size to 5% of the speed of light and then decelerate it at the destination would require roughly 10,000 years worth of that total United States energy output, focused into a single launch. 10,000 years of electricity. For one ship, chemical rockets don't come close. Their fuel releases energy through chemical reactions, the same basic process as burning wood or gas, just faster and hotter. The energy density of even the best chemical fuel is millions of times too low for interstellar requirements. Nuclear fission, the process that powers current reactors by splitting heavy atoms, releases about 1,000,000 times more energy per kilogram than chemical fuel. That sounds like enough. It isn't. Even with a perfect nuclear fission drive, getting a large crewed ship to 5% of the speed of light would require a mass of fission fuel that exceeds what any launch system could carry. Nuclear fusion, the process that powers stars by merging light atoms, releases even more energy per kilogram. A fusion drive, if one could be built, would dramatically improve the fuel efficiency. Scientists have pursued fusion power for decades. As of now, no fusion reactor has produced more energy than it consumed in a sustained reaction. It remains the energy source of the future that hasn't arrived yet. Antimatter drives appear in every science fiction story about fast space travel, and the physics behind them is real. When matter meets antimatter, both are converted entirely to energy with 100% efficiency. No other process produces more energy per kilogram of fuel. A ship powered by matter-antimatter annihilation could theoretically reach a large fraction of the speed of light with a manageable fuel mass. The catch: producing antimatter requires more energy than it releases. We currently produce a few nanograms of antihydrogen per year in particle accelerators at enormous energy cost. Producing enough antimatter to fuel an interstellar mission would require an accelerator complex the size of a solar system and thousands of years of operation. Every energy source that could theoretically power interstellar travel runs into a wall when you try to actually build it. The math is honest. The physics is clear. The energy exists in the universe. Capturing it, storing it, and directing it toward a spacecraft in a practical way remains the central unsolved engineering problem of our time. And the energy to move the ship is only one part of the problem. The energy to keep the people aboard it alive for decades is a completely separate challenge. The ship is moving, the crew is alive, everything is functioning, and the human body is already starting to break down. Space is hostile to biology in ways that take time to reveal themselves. Astronauts on the International Space Station, spending only 6 months in low Earth orbit, return to the surface with measurable physical changes. Bone density drops, muscle mass decreases, the spine lengthens slightly as discs expand without gravity compressing them. Fluid that normally pools in the legs shifts toward the head, altering vision and putting pressure on the brain. 6 months does that. A journey through the Kuiper belt and toward another star would take decades. Bone loss in microgravity happens at roughly 1 to 2% per month without countermeasures. Exercise programs on the International Space Station slow the process but don't fully stop it. Over years in space, the skeleton weakens to a point where re-entry and planetary landing could cause fractures just from the physical stress of deceleration. Muscle atrophy follows a similar curve. The heart, which is itself a muscle, weakens in microgravity because it doesn't need to pump blood upward against gravity. A crew member who spent 20 years in space and then tried to stand on a planet's surface would face potential cardiovascular collapse. Radiation is the other assault. Inside Earth's magnetic field, we're protected from most cosmic rays and solar particle events. Beyond the heliopause, that protection disappears. Cosmic rays, high-energy particles accelerated by distant supernovas, pass through spacecraft walls and through human tissue, damaging DNA at the cellular level. Over years, that damage accumulates. The risk of cancer climbs significantly. So does the risk of damage to the central nervous system, a concern that scientists only began documenting recently through data from long-duration spaceflight studies. A 20-year mission outside the heliosphere would expose a crew to cumulative radiation doses that exceed every current safety limit by large multiples. The acceptable lifetime radiation dose for an astronaut set by health agencies would be surpassed within the first few years of such a journey. Psychological stress is less measurable, but equally real. Studies of isolated human groups in extreme environments, Antarctic research stations, long submarine deployments, and spaceflight simulations show consistent patterns. Irritability increases. Group cohesion frays. Depression and anxiety become harder to manage. Sleep disruption affects judgment. A crew sealed in a ship for 20 years with no resupply, no reinforcements, and no way to leave would face psychological pressures that no mission training has ever prepared humans to endure at that scale. There is also the question of time. If a crew left Earth in their 30s, they would arrive at their destination in their 50s. They would have spent more than half of their adult lives in a metal container moving through the dark. Whatever they left behind on Earth, families, relationships, the world they knew, would have changed beyond recognition. The human body is built for a planet. It evolved over millions of years under gravity, under a cycle of light and dark, under conditions that deep space eliminates entirely. Getting the ship there is one problem. Keeping the people inside it alive and functional for the duration is a separate problem that medicine hasn't solved yet. The crew is 30 billion miles from Earth. Something has gone wrong. A pipe has burst in the water recycling system. The repair requires a decision between two approaches, and one of them risks damaging a secondary system that powers half the ship's heating. The crew needs advice from the engineering team on Earth. They send a message. It travels at the speed of light. 5 hours later, it arrives on Earth. Engineers read the message, run the analysis, consult the specialists, write a detailed response. 5 hours later, that response arrives on the ship. 10 hours have passed. The water system is still broken. The decision still hasn't been made. And if the pipe was spreading contamination through the water supply the whole time, 10 hours of waiting may have made the problem significantly worse. This is the communications blackout reality of deep space. The International Space Station communicates with Earth in near real time. Signal delay measures in fractions of a second. Mission controllers can watch telemetry data as it happens, catch problems forming before they become crises, and talk a crew member through a repair step by step. At Kuiper belt distances and beyond, every one of those capabilities disappears. The crew becomes entirely self-sufficient. By necessity, every decision, every repair, every medical emergency, every navigation question, every equipment failure falls on the people aboard. They carry no specialist they can call, no doctor beyond whatever training they received before launch, no backup team that can step in. Spacecraft are built with redundant systems for this reason, and those redundancies are vital. But redundancy only covers scenarios that engineers anticipated during design. Real emergencies, the kind that actually kill crews, tend to be the ones nobody planned for. Apollo 13 is the most famous example. An oxygen tank explosion created a cascade of failures that mission controllers and crew had to solve together in real time, under pressure, using equipment that was never designed for that situation. The communication delay between Earth and the Moon runs under 3 seconds. That 3-second window was small enough to allow real collaboration, 3 seconds versus 10 hours. The communications gap also affects mission planning in a deeper way. A crew that far from Earth carries the full weight of every decision with no safety net of consensus. Disagreements between crew members about risk assessment, about resource use, about priorities have no outside authority to appeal to. Whatever hierarchy exists aboard the ship is all there is. History of long-duration isolated missions, even on Earth, shows that group dynamics under stress become one of the central threats to mission success. Antarctic winter-over teams, submarine crews, and long-duration spaceflight simulations all document the same pattern. Interpersonal conflict under prolonged isolation is not a soft problem. It's a survival problem. A crew 10 light hours from Earth arguing about a critical repair decision in the middle of a failure cascade has no one to break the deadlock. The distance that makes deep space travel slow also makes it lonely in a way that goes beyond the poetic. It's operationally lonely, technically lonely, the kind of alone that means every mistake carries consequences that cannot be undone by calling for help. Past the Kuiper belt, the help simply doesn't arrive in time. The Kuiper belt ends around 4.5 billion miles from our star, but the solar system doesn't. Beyond the Kuiper belt lies a region so vast and so poorly understood that scientists still debate its basic structure. It's called the Oort cloud, and if the Kuiper belt is the outer wall of a house, the Oort cloud is the property line that extends for miles in every direction around it. The Oort cloud is believed to be a spherical shell of icy objects surrounding the entire solar system, extending from roughly 2,000 astronomical units all the way out to perhaps 100,000 astronomical units. 1 astronomical unit is the distance from Earth to our star, about 93 million miles. 100,000 times that distance is close to 2 light years, nearly halfway to the nearest star. Scientists have never directly observed the Oort cloud. Its existence is inferred from the behavior of long-period comets that take hundreds or thousands of years to complete a single orbit. These comets arrive from random directions, unlike the comets in the Kuiper belt that orbit in a relatively flat disk. The only structure that explains random arrival directions is a spherical shell. What disturbs Oort cloud objects into long falling orbits toward the inner solar system is still not fully understood. Passing stars, the gravitational influence of the galaxy's mass, and possibly the same undiscovered large body that drives Planet 9, speculation, have all been proposed as triggers. The transition zone between the outer Kuiper belt and the inner Oort cloud is itself unclear. Some researchers believe there's a scattered disk of objects between the two, a dynamically chaotic region where objects from both zones mix. Other models suggest the transition is gradual rather than sharp. The actual density of objects across this region remains unmapped. For a spacecraft heading toward another star, this matters enormously. The outer Kuiper belt already presents navigation and shielding challenges. The transition into the Oort cloud adds a zone of almost complete uncertainty. Scientists don't know the density of objects in that region. They don't know the size distribution of the particles and bodies there. They can't provide a reliable map because no mission has ever traveled that far and reported back. The Voyager probes are still traveling outward and are expected to spend tens of thousands of years crossing the Oort cloud if they maintain their current trajectories. They send back data, but their instruments weren't designed to survey the Oort cloud region specifically, and their signal strength weakens with each passing year. Any ship leaving the solar system would spend longer inside the Oort cloud than it spent crossing the Kuiper belt. Far longer, and the entire time it would be doing so without any reliable map of what lies ahead. Scientists don't know what density of particles a ship moving at high speed would encounter. They don't know whether the Oort cloud contains localized regions of higher concentration that could increase impact risk dramatically. The Kuiper belt is at least partially mapped. The Oort cloud is a theoretical structure inferred from shadows and echoes. And between the outer edge of the Oort cloud and the nearest star, there lies something that makes even the Oort cloud seem familiar and well understood. The Kuiper belt has been studied for over 30 years. Hundreds of objects have been catalogued. Several have been photographed up close. Scientists have published thousands of papers on its structure, composition, and history, and the fundamental questions about its population remain open. The total number of Kuiper belt objects larger than 60 miles across is estimated at roughly 100,000. That number comes from careful telescope surveys combined with mathematical models that account for objects too dim or too distant to detect directly. Below 60 miles, the estimate becomes genuinely uncertain. Objects smaller than that reflect too little light at this distance to be reliably detected by current instruments. Scientists extrapolate from the size distribution of larger objects, assuming that the same mathematical pattern holds as size decreases. But that assumption hasn't been directly tested. The actual population of smaller objects could be higher or lower than models predict. This matters for spacecraft. A ship crossing the Kuiper belt faces risk primarily from objects in the range it can't easily track. Fragments smaller than a house, but larger than a sand grain, moving in orbits that haven't been mapped. The large objects are catalogued well enough to avoid. The microscopic particles are everywhere but individually harmless at low speeds. The middle range, meter scale and smaller fragments, represents the hardest hazard to quantify. The total mass of the Kuiper belt adds another layer of uncertainty. Current estimates suggest the belt holds between 4 and 10% of Earth's total mass, but researchers acknowledge that the actual number could fall outside that range, depending on the true population of small objects. The shape of the belt itself contains surprises. Astronomers identified a region called the Kuiper Cliff, a sharp drop-off in the number of objects detected beyond about 50 astronomical units. Models of how the outer solar system formed predict that objects should continue to exist at similar densities beyond that boundary. They don't. Something removed the material, or the models are wrong. Planet 9's hypothetical gravity is one proposed explanation for the cliff. Another is that the outer belt was cleared by a passing star early in the solar system's history. A third possibility is that the objects are still there, but too cold and dark for current telescopes to find. The Vera C. Rubin Observatory designed to scan the entire visible sky every few nights, was expected to dramatically improve the census of outer solar system objects once it reached full operation. Every new object detected refines the population model. Enough new data could resolve the Kuiper Cliff mystery, detect Planet 9 if it exists, and give mission planners a far more accurate picture of what lies in the path of any future deep space mission. Until then, every spacecraft sent through the belt operates on incomplete information. Engineers account for this by building probability margins into mission designs. If models suggest a certain debris density, the ship is built to handle somewhat higher than that. The margin isn't generous because generous margins cost mass, and mass costs everything in space. The belt keeps its population count secret. Every new telescope generation reveals a few thousand more objects and leaves millions more undetected. For mission planners, designing a safe path through a hazard zone you can't fully map requires a level of confidence in incomplete data that keeps everyone involved quietly uncomfortable. The nearest star to our own is called Proxima Centauri. It sits roughly 4.2 light-years away. A light-year is the distance light covers in 1 year, traveling at 186,000 miles per second every second for 365 days. 4.2 light-years means light takes 4 years and about 2.5 months to cross that gap. Now compare that to our fastest machine. New Horizons travels at roughly 36,000 miles per hour. That speed, held constant without any further acceleration, would carry the probe across the distance to Proxima Centauri in approximately 75,000 years. Some calculations place the figure slightly higher, around 80,000 years, depending on the probe's exact trajectory. 75,000 years ago, modern humans were living in small groups across Africa, Europe, and Asia. Agriculture hadn't been invented. Writing didn't exist. The oldest known cave paintings were only beginning to be made. If New Horizons had been pointed at Proxima Centauri and launched at that moment in human prehistory, it would be arriving roughly now. That comparison does something useful. It pulls the number out of abstraction and drops it into something the human brain can actually feel. The technology gap between what we have and what we need is not a small engineering problem waiting for a clever fix. It's a difference of several orders of magnitude in fundamental capability. To cross to Proxima Centauri in a single human lifetime, say 80 years, a spacecraft would need to average roughly 5% of the speed of light throughout the journey. That's about 33 million miles per hour, nearly 1,000 times faster than New Horizons. To make the crossing in 20 years, as the Starshot project proposes for its chip-sized probe, the vehicle needs to reach 20% of the speed of light, about 130 million miles per hour, over 3,000 times faster than anything humans have ever launched. Every proposed technology for achieving those speeds, nuclear pulse drives, fusion rockets, antimatter engines, laser sails, faces barriers that are either engineering challenges requiring decades of development or fundamental physics limits that current science hasn't found a way around. The closest any mission has come to changing that picture is the Parker Solar Probe, which reached roughly 400,000 miles per hour during its closest approach to our star. That's more than 10 times faster than New Horizons, and it's still less than 1% of the speed needed for a practical interstellar mission. The gap is real, the gap is large, and it persists despite decades of serious scientific attention. What makes this more than an abstract problem is what it means for the future. Humanity has never lived on a world other than Earth. Every human who has ever existed was born and died on this one planet. The ability to reach another star system, to establish any presence beyond this solar system, depends entirely on solving a problem that currently has no solution anyone can build. The 75,000-year number isn't a reason to give up. It's a measure of how far the work has to go, and the technology to change that number may already exist in concept form, waiting for the energy and materials science to catch up. Sunlight pushes things. This sounds wrong. Light feels weightless. It warms your skin, but it doesn't knock you over. Yet the physics is confirmed. Photons, the particles of light, carry momentum. When a photon strikes a surface, it transfers a tiny push. This effect, called radiation pressure, is measurable and real. In everyday life, it's far too small to notice, but in space, where there's no friction and no air resistance, even a tiny continuous push adds up over time. A light sail is a spacecraft that uses this pressure as its engine. A thin reflective surface catches incoming light. The photons bounce off and transfer their momentum to the sail. The sail, and anything attached to it, begins to accelerate. The idea dates back centuries. Johannes Kepler observed that comet tails always point away from our star, regardless of the comet's direction of travel, and correctly reasoned that something from the star was pushing on them. He was describing radiation pressure in 1619. The first successful test of a solar sail in deep space was the Japan Aerospace Exploration Agency mission Icaros, launched in 2010. It deployed a sail about 46 feet across and confirmed that solar radiation pressure could both accelerate the craft and be used for steering. It worked. The physics held, but sunlight alone becomes too weak to be useful past the inner solar system. By Jupiter's distance, it's already dramatically weaker. In the Kuiper belt, it's nearly useless. Breakthrough Starshot's proposal replaces sunlight with a laser. A ground-based laser array fires a concentrated beam at an extremely thin sail, smaller than a postage stamp, but spread across several meters of reflective material, only a few hundred atoms thick. The laser is thousands of times more intense than sunlight. The sail, being nearly weightless, responds to even this concentrated push and accelerates rapidly. The acceleration phase lasts only a few minutes. During that window, the probe reaches 20% of the speed of light. After that, the laser can no longer reach the sail accurately as the probe moves outward, and the ship coasts the rest of the way. The sail material proposed for Starshot needs to reflect the laser almost perfectly. If it absorbs even a small fraction of the beam's energy, it would overheat and vaporize instantly at the power levels involved. Current candidates include thin films of silicon nitrogen with highly reflective coatings. Testing these materials at the required power levels hasn't been fully achieved. The laser array itself presents a challenge of coordination. A single laser powerful enough to do the job would be impractical to build. The Starshot proposal calls for thousands of smaller lasers that fire simultaneously, with their beams focused precisely on the same point. Keeping thousands of lasers aligned on a sail moving at increasing speed across a changing position requires control systems that don't exist yet. The project has received funding and serious scientific attention. Research into the necessary components continues at universities and laboratories around the world. The concept is sound. The engineering is decades away from ready. And even if it works, it only works for objects the mass of a postage stamp. Every problem that makes crossing the Kuiper belt hard also exists in magnified form between our solar system and the nearest star. Temperature, distance, communication delay, radiation, microparticle impacts, energy requirements, navigation uncertainty, human biology under long-duration exposure to space. The Kuiper belt doesn't create unique challenges, it introduces them. It's where you first encounter each barrier at a scale that matters, where you first discover whether your ship, your technology, and your crew can handle what comes next. Think of the Kuiper belt as the first real test of any deep space mission design. If a ship can cross the belt with its systems intact, its crew healthy, its fuel reserves sufficient, and its navigation accurate, it has passed the opening exam. What lies beyond is the same exam, scaled up by factors that strain comprehension. The particle impacts that chip away at a hull in the Kuiper belt continue through interstellar space, where the particles are slower but the journey lasts centuries instead of years. The communications delay that reaches 10 hours inside the belt grows to years once a ship moves into true interstellar space. The radiation environment that increases beyond the heliopause worsens with every light year traveled. The Kuiper belt is also where human biology first hits its limits. 6 months on the International Space Station produces measurable physical changes. A journey through the Kuiper belt would take years. The bone loss, muscle atrophy, radiation exposure, and psychological strain that begin accumulating inside the belt would compound over the full duration of an interstellar voyage. Here's the part that rarely gets discussed. The Kuiper belt is the last place where Earth can still help. A crewed mission to Mars benefits from communication delays of only a few minutes. A mission to the asteroid belt faces delays of up to 20 minutes. Even a mission to Jupiter deals with communication times under an hour. In all those cases, Earth-based teams can still play a meaningful role in managing emergencies, providing real-time guidance and supplying information that helps crews make decisions. The Kuiper belt is where that support stops being meaningful. At belt distances, even the fastest signal takes several hours each way. A crisis on a ship in the belt unfolds and resolves before Earth can respond. Everything beyond the belt exists in a state of permanent operational independence. That's why the Kuiper belt matters as a target and not just an obstacle. Any technology, any life support system, any propulsion system, any navigation method that works across the full width of the Kuiper belt has demonstrated something important. It has shown it can function without real-time support. It has shown it can handle the cold, the particles, the radiation, the isolation. The belt is the testing ground, the first wall, the place where every deep space dream meets the first version of the physics it will eventually have to defeat on a far larger scale. Solving the Kuiper belt crossing doesn't mean solving interstellar travel, but failing to solve it means never getting the chance to try. The rocket that burned chemical fuel got us to the moon. It won't get us to the stars. Every serious proposal for interstellar travel requires a fundamentally different approach to generating thrust. Here's where the leading ideas actually stand. Ion drives are the most mature technology beyond chemical rockets. They work by accelerating electrically charged particles backward to generate thrust. The exhaust velocity is far higher than any chemical rocket, which means the same amount of fuel produces more speed over time. NASA has flown ion drives successfully on multiple missions, including Dawn, which orbited 2 asteroid belt bodies. The limitation is thrust. Ion drives are efficient but gentle. The force they produce is tiny, similar to the weight of a sheet of paper against your hand. Accelerating a large crewed ship to even 1% of the speed of light with current ion drive technology would take decades of continuous operation and enormous amounts of electrical power. They work for small probes on long missions. They can't scale to human interstellar travel with current designs. Nuclear pulse propulsion was seriously studied in the 1950s and 60s under a project called Orion. The concept was blunt and brilliant. Detonate a series of small nuclear bombs behind the ship, let the plasma push against a large plate at the stern, and ride the explosions forward. Mathematical models confirmed the approach could reach several percent of the speed of light with a large enough ship. The project was cancelled for political reasons. No nuclear detonation propulsion system has ever been tested in space. The engineering challenges of building a ship that survives thousands of nuclear detonations and the international treaties that ban nuclear explosions in space have kept the idea theoretical. Nuclear fusion drives represent the next step up. Fusion releases energy by merging light atomic nuclei, the same process powering stars. A fusion engine would produce far more thrust per kilogram of fuel than fission or chemical systems. Scientists have pursued controlled fusion for over 70 years. Several major projects, including the International ITER reactor under construction in France, are working toward a sustained fusion reaction. As of current data, no fusion reactor has produced more energy than it consumes. A fusion drive for spacecraft remains theoretical until that fundamental barrier is crossed. Antimatter engines exist only in physics calculations and engineering proposals. The energy released when matter and antimatter annihilate is the highest energy density possible in the known universe. A ship powered by antimatter annihilation could theoretically reach relativistic speeds with a manageable fuel mass. The barrier is production. Creating antimatter requires particle accelerators and produces only nanograms per year at current facilities. At enormous energy cost, scaling to mission-relevant quantities is not an engineering problem. It's a civilization-scale infrastructure problem that would take centuries to solve. The laser sail approach proposed by Starshot sidesteps propulsion entirely by leaving the engine on Earth. That's its most elegant feature and its greatest limitation simultaneously. It works for tiny probes. It can't carry a crew. None of these technologies is ready. Some are decades away from ready. Some may never scale to crewed missions with current understanding of physics. The honest assessment is that humanity has identified the problem and proposed solutions, but the solutions remain either unbuilt, unproven, or physically blocked by barriers that current science hasn't crossed. The path forward requires breakthroughs, not refinements. And breakthroughs, by definition, arrive on their own schedule. Every frontier humanity has ever crossed felt impossible beforehand. The first sailors who left sight of land had no maps of what lay beyond the horizon. The first pilots who broke the sound barrier flew in vehicles that engineers predicted would shake apart. Every boundary that looked permanent turned out to be temporary, given enough time, enough failure, and enough people who refused to treat the boundary as final. The Kuiper belt is the current boundary. It sits at the edge of what our technology can reach with unmanned probes, and far beyond what we can reach with human beings. The distance, the cold, the radiation, the particles, the communication delay, the energy requirements, the biological limits of the human body. Every challenge described across these chapters is real, confirmed by physics, and currently unsolved at the scale a crewed mission requires. And yet, none of them violate the laws of physics. That distinction matters enormously. A barrier that breaks the laws of physics is truly impossible. A barrier that sits within those laws but exceeds current technology is an engineering problem. Hard engineering problems get solved. They get solved slowly, expensively, with many failures, and often in ways nobody predicted in advance. But they get solved. The materials needed for adequate shielding at relativistic speeds don't exist yet. But material science has produced extraordinary advances in the last century, from aluminum to carbon fiber composites, to aerogel, to graphene. The pattern of discovery hasn't slowed. The energy needed for fusion propulsion hasn't been achieved in a controlled setting yet, but the physics of fusion is understood, and the engineering gap between current reactors and a working fusion drive, while enormous, is measurable. The biological challenges of multi-decade spaceflight haven't been solved, but each year of research on the International Space Station adds to what scientists know about how to protect a human body in space. Every piece of the puzzle is being worked on. The Kuiper belt won't be crossed by a human crew this century, almost certainly. The barriers are too high and the technology too far behind. But the trajectory of progress, the direction it's heading, points toward a future where those barriers are cleared one by one. The first crewed mission to cross the Kuiper belt, whenever it happens, will mark something more significant than a technical achievement. It will mark the moment humanity stopped being a single-planet species, in a practical sense, and became something that could operate independently of Earth's immediate neighborhood. Everything after that, every star, every system, every world in the galaxy, becomes reachable in principle. The Kuiper belt is the gate, and gates, no matter how heavy, exist to be opened. The universe is enormous, silent, hostile, and indifferent. The stars don't care whether we reach them. The cold and the dark and the distance don't bend for ambition. But every time humans have stood at a wall that looked permanent, someone eventually figured out where the door was. The door is out there, past the frozen ring, past the Oort cloud, past the gulf between stars. We just haven't built the key yet.